Thank you everyone for coming to our last Lunch and Learn of 2025. I'm Inarelli Morales. I'm the Air Quality Policy Analyst in Weld County in the Public Health Department. I'm also the Secretary of the Rocky Mountain State section of the Air and Waste Management Association. And so today we're super excited to have Rachel Greene speak to us about indoor air quality and the role surfaces have on that. Rachel is a PhD candidate in analytical chemistry at Colorado State University under Dr. Delphine Farmer. Her research focuses on the role surfaces have in indoor air quality, specifically the size of surface reservoirs and the partitioning behavior of surfaces. She uses a variety of analytical instruments adapted from material science and ecology in both lab and indoor field experiments to obtain direct measurements of indoor surfaces. Rachel earned a Bachelor's of Science in Chemistry at George Washington University, and her undergraduate research involved improving ground-based measurements of greenhouse gases. Rachel is also a, what do we call it, honorable mention for our RMSS scholarship program. So it was amazing to hear about all the awesome stuff that Rachel is doing. If you have questions, feel free to put them in the chat, but we will get to those at the end of the presentation. So Rachel, take it away.
Awesome. Thank you so much for the introduction, and thank you for having me here. It's quite an honor to be able to present today. As mentioned, my name is Rachel Greene, and I'm going to be talking about the role surfaces have on indoor air quality. And when I talk about surfaces, I literally mean the surfaces up above you, on your ceiling, on your floor, and the desk right in front of you, and how that's impacting the air you're breathing right now. And we really care about indoor air quality, and it's a stat probably many of us have heard, but we spend 90% of our time indoors, and so we want to understand our exposure on a day-to-day basis. Most of air quality studies have focused on outdoor environments, but the indoor environment is quite different. And there's some key differences I want to highlight. One is the surface area. So we have these surface area to volume ratios at the bottom here. And these ratios have surface area divided by the volume of gas in a given area. And so outdoors, typically we think of the surface area of aerosols. That is 1 times 10 to the negative 3 meters inverse, while indoors, that's typically 3 plus or minus 1 meters inverse. And so that's 3 orders of magnitude greater surface area. So we're going to see a lot more multi-phase chemistry, and surfaces play a larger role in an indoor environment versus an outdoor environment. There's also differences in compounds and how these compounds behave. So compounds are typically volatile outdoors, or as we behave semi-volatile indoors. And so an example I like to bring up is like nicotine. Typically outdoors, we expect nicotine to be in the gas phase, but inside, we actually consider nicotine to be quite a sticky substance, primarily being found on our surfaces. And so nicotine itself is going to undergo different chemistry because it's going to be found on the surfaces indoors versus how it's going to behave outdoors. Another key difference is the oxidants. There are some shared oxidants like hydroxyl radical and ozone, but outdoors, we typically care about the hydroxyl radical, and indoors, we care a lot about how ozone and how what oxidation chemistry comes about from ozone reactions. There's also some unique oxidants indoors. And so one is nitrous acid, also called HONO. That's typically going to be found from gas stoves or created on surfaces. When NOx comes indoors, it can undergo some acid-based chemistry and create HONO. And so that's a unique oxidant indoors that we don't see outdoors that can really impact the chemistry that's occurring. And so if we take a broader picture of the indoor environment, it can be quite complex. There's various sources and sinks that really impacts indoor chemistry and our indoor air quality. And I'm really just focusing on one aspect of it, which is the surfaces and the building materials. But I hope by the end of this presentation, you see that this is a really important aspect that we need to focus and understand in order to improve our air quality. And so I want to talk about how we know right now how surfaces impact air quality. One way is that new indoor surfaces can emit known contaminants. So something like wallboard, in this example, we had formaldehyde emitting off. Wallboard can emit formaldehyde. Paint also tends to, when we freshly paint surfaces, they emit VOCs. And so that's one way in which surfaces can impact indoor air quality. Surfaces can also have the sink source behavior. So they can first absorb semi-volatile organic compounds, or they can diffuse into some surfaces that have that are permeable. And then these surfaces can store certain materials. So on the surface, we can consider for absorption the surface area, or for, again, these permeable bulk surface materials. They can have this absorption or bulk capacity. And then some of these gases are actually going to slowly re-emit over time that can impact the air that we're breathing. So this is typically when we think about third-hand smoke, the cigarette smoke goes to the surface and then they slowly re-emit over time. And then surfaces can also have reactions on them. And so bringing up one of my favorite examples of nicotine, when we know that it likes to be on the surface and it likes to react, in this case with HONO, which is unique to the indoor environment, and they create these nitrosamines, which are known to be carcinogenic. And so this is one reaction in which surfaces mediate, causing more harmful contaminants than just the ones that are coming from different emission events. And so when we talk about surfaces, I tend to use surfaces and surface reservoirs interchangeably, but I'd like to just define what we call surface reservoirs. And these are all the collective ways in which gases interact with surfaces. One, they can absorb into the interfaces. They can also create these surface films. And so surface films are just these multi-layer absorption that's occurring, and they could be nanometers thick. And so they can also be aqueous or organic. And so depending on that, they can have different chemistries. They can diffuse into pores. Particles can also deposit onto surfaces that can impact surface film formation or other aspects of chemistry. And then for some materials, it can also diffuse through the solid and into the bulk material. And that diffusion actually notes a key difference between two indoor surface types. We have impermeable surfaces, which do not have that bulk diffusion that's occurring, and permeable surfaces that do have that bulk diffusion. And so we could think of something like glass made from like our windows as an impermeable surface. We're not having that diffusion happening at relevant timescales where we actually see diffusion to occur. And something permeable like the ceiling tile, the ones that the classic drop ceiling, as a permeable surface is quite spongy, it's going to absorb a lot of that material. And so we know surfaces play a major role in indoor air quality through these observational field campaigns. And so this one study in particular was measuring background gas phase concentrations of different gases. And then what they decided to do is open all the windows and doors. And when doing that, they see a decrease in background levels. That's because there's enhanced ventilation. But when they close all the windows and doors, they see a return back up to the background level. And that return, the response time from the study, they calculate that it must be coming from a large source, and that source is likely surfaces. And this repeatedly happens throughout the day. So it's not only that it happens once or twice, but these surfaces store enough of these compounds to actually constantly re-emitting back to the background phase after we do all these enhanced ventilations. And so it really shows that these surfaces are storing a lot and impacting the background levels in which we're breathing. And like mentioned, that the surfaces can act like a source and a sink, and that changes over time. So this was a study done by our group. And what we did was expose the emission event of wildfire smoke. And that's going to be the blue line is one just a VOC from wildfire smoke. And then the dotted line is the ventilation rate. And so immediately after the event, you're going to have more absorption than desorption. And so that's where the surfaces are primarily acting as a sink. It's improving indoor air quality because it's eating up the gas phase concentration. At this adsorption desorption equilibrium point, that is when the decay rate of the VOC smoke is equal to the ventilation rate. And so these surfaces are having equal rates of adsorption and desorption. So it's equally acting like a source and sink. It's not really impacting indoor air quality. And to that point, after that point, we will primarily have desorption happening. But that desorption only ends up negatively impacting our air quality after this ACR air change rate, also could be called ventilation rate. After that point, that's when desorption or surfaces are actually then impacting the air we breathe. And that timeline can go on for hours to weeks to even months that this decay can last, negatively impacting our air quality depending on what gas molecule we are looking at. And so knowing that these surfaces can impact the air we breathe due to this partitioning behavior, what actually determines or controls gas surface partitioning? One thing, as I mentioned, is the chemical properties of the gas compound, in particular, the octanol air partitioning coefficient. And so that is basically how much the gas prefers to be in an organic phase, which is represented by octanol, versus the air phase. And so between that, the higher the KOA, the more likely it's going to be found in surfaces. So compounds that have higher KOAs are going to be more likely partition to surfaces and then desorb, take longer to come out of the surface, thus having a longer impact on our air quality. Surface area also impacts gas surface partitioning. Surface area volume ratios, as I mentioned, are used to understand the transport, transformation, and fate of gases and particles. And the more surface area indoors, the more area available for absorption, and thus more the surfaces can store. And when surfaces can store more, the more they can emit over time. And so it's important to understand the surface area indoors so we understand the capacity of our surfaces. The surface itself, other physical properties and chemical properties can impact gas surface partitioning. So there's a thing called chemiabsorption, which is the chemical bond between the surface and the gas phase chemical. And so some surfaces, such as polyester, synthetic carpet, like such as a polyester, is going to prefer non-polar chemicals, gas phase chemicals, over a polar one. And so that's going to change what kind of absorption behavior we're seeing indoors. Some gases might be found more on certain surfaces versus other surfaces. Pores can also enhance diffusion. As I mentioned, diffusion can cause molecules to go into the bulk material, and that's going to then increase how much is being stored. And so there's three types of diffusion that primarily happens. We have the solid state diffusion, which is going to be the slowest, and we typically see that in polymers like paint. But then there's other surfaces that have a lot of pores. Again, you can, the ceiling tiles with all those holes are ones I like to think of most commonly. There's molecular diffusion and Knudsen diffusion, both that have gas phase diffusion. So it's going to be quicker than a gas going through solid. However, there's a slight difference between the two. Molecular diffusion is going to be the fastest, and that's because the pores are so large that the gas molecules are primarily interacting with each other. So they're just almost like it's in the air phase and they're just diffusing through the solid. Knudsen diffusion is going to be a bit slower than molecular diffusion because in smaller pores, they're going to end up colliding with the pore wall, slowing down the rates a bit. And so knowing all these different factors that impact indoor air quality, I'm going to get a little more in the specifics on the surface side of these. And so with surface area, back to surface area, these measurements that measure surface area typically use geometric surface area. And we define geometric surface area as the dimensional surface area of the surface. So you take this glass slide and it's 3 by 1 inch. It has a geometric surface area of 3 inches squared. This piece of carpet, I'm going to say it's 2 by 2 meters. And so it has a geometric surface area of 4 meters squared. However, with topographical images I've taken, we can see that these surfaces aren't these perfectly smooth materials that we can say have that surface area. They're actually quite textured. Glass looks quite insane, but the roughness is actually still considered fairly smooth on a manufacturing scale. But when we look down at carpet, the roughness is almost 9 nanometers with a scale going up to almost 40 nanometers. And so that's going to add surface area that's just not accounted for when we use geometric surface area. And that can actually increase what we think the capacity of surfaces is more than what we've actually been using in the literature. We also, because of the physical and chemical properties of surfaces, no surfaces behave differently. And so I'm going to go through a series of chamber experiments to demonstrate how we know this. And so in these chamber experiments, what they did is they put a surface inside a chamber and they expose it to a gas phase compound and see how the decay happens. And so in this particular example, they put wallboard and exposed it to ethyl benzene. And they had 2 different models to try to describe the behavior. They had the no-sink model, which does not fit the data points, and no-sink basically says that the wallboard is not interacting with the gas phase compound. We know that's not true from many of our different studies. Then we look at this adsorption model, which is Langmuir adsorption, just a type of adsorption. And now we see that that fits the data a lot better. And we're just saying that these gas compounds are absorbing to the surface, also able to desorb from the surface. However, when they looked at another surface material, so they looked also at carpet, they see that the data there doesn't necessarily fit either one of these models. So with carpet, we can't necessarily say only adsorption is occurring. There has to be some other phenomenon happening. And so something about carpet is different than wallboard. A study in the future decide to incorporate diffusion into this model and see how that impacts how the model fits. And they saw that actually improves the fit quite a bit. And so this diffusion is uniform diffusion throughout the surface. And so now that we see this data fits a lot better. And so some surfaces are going to have diffusion, some won't. However, this is a model. We're assuming a certain type of diffusion, and we don't know if maybe another type of diffusion is happening better. As we mentioned, pores can impact diffusion. So how, if we think about diffusion differently, does model fit differently? And so this other study, this wasn't so much a chamber study as looking at a collective all the surfaces in the room, and they saw that certain compounds show non-uniform diffusion. So the rates that they're diffusing in is actually diffusing out at a different rate. And so with that, how do we know the exact partitioning behavior from surfaces from these models and gas phase measurements, we need to directly measure these surfaces instead to actually understand what's the partitioning behavior going on. And that kind of leads into the key research areas I care about, which is measurement of specific surface area. Porosity and roughness. Specific surface area is defined as the total area of a surface. So if you, it's all the areas in which a gas molecule can absorb to a surface. And so it gives a better description on the surface area available for absorption versus a geometric surface area. We also know porosity impacts diffusion, and then roughness can also have various impacts. I also want to explore molecular absorption and diffusion on surfaces, and primarily by getting these direct measurements, so I can understand the details of the diffusion and absorption that's happening instead of trying to infer gas phase measurements on that behavior. I also want to evaluate the absorption capacity of permeable surfaces. So how much can the bulk material store? There's been very few studies that have actually been able to try to address this absorption capacity, and it's largely because the bulk material of many surfaces are hard to study, and we lack direct measurements of these indoor surfaces. And so my research is part of a broader project called the Keck Indoor Biogeochemical Project. And so it has three major aims that this project's trying to address with various graduate students and research scientists and PIs trying to understand indoor chemistry better. The first is understanding the cycling of reactive organic carbon compounds across gas, aerosol, and surface phases as a function of location and time. In particular, I'm caring about the surface phase and really trying to develop a way to better understand the surface side of indoor chemistry. It's also to understand the timescales and extremes of speed for indoor chemical transformations. And in particular, while a lot of these instruments, we have a lot of online instruments that can have really high resolution, I'm actually caring about the longer timescales of how long do these surfaces re-emit over months and like weeks instead of like a high second basis on the resolution. And the measurements I'm hoping to help with the third aim of to generate a new predictive multi-phase model of indoor chemistry that allows to take our measurements from direct observations to predictive capacity, which is ultimately our goal as a chemist, is to have our measurements be used in models to help improve indoor air quality and other aspects. And so how this project has been run is that we have a real office space that we are able to test the indoor air quality and other chemistry that's occurring. And connected to there, we have all these online instruments, various gas and aerosol instruments, such as trace gas instruments, different chemical ionization mass spectrometers, and we are able to measure in real time the different gas and aerosol phase. What I do is typically put my surfaces in the room and remove them and use two different mass spectrometers to understand the chemistry that's occurring. I use an isotope ratio mass spectrometer to quantify what's in the surface and a direct analysis in real time mass spectrometer to get some qualitative data on oxidation products. Though, to actually do our experiments, we have a VOC injection system, and there is a heated line that we can inject different compounds into the room. And in particular, what makes this project unique is that we use isotopically labeled compounds. And so these are ones that have a specific carbon-13 or nitrogen-15 or oxygen-18. And by doing that, we can actually trace the different reactions occurring, like such as if we have 18O, we can see what that ozone is reacting with. Or in my case, if we inject something with carbon-13, I can see them in my surfaces. So these are all the little isotopically labeled gas molecules in the room undergoing a lot of different chemistry, whether it's multi-phase chemistry or partitioning. I also care about the physical properties. And so there's been two other methods I've been using to understand the physical properties of the surface. One is the BET specific surface area analyzer, and that measures the porosity and specific surface area of a surface using gas absorption. And when it comes to porosity, there's three pore sizes that we care about: the micro, which is less than 2 nanometers, meso 2 to 50 nanometers, and macro, which is greater than 50 nanometers. And in particular, the BET specific surface area analyzer measures a pretty wide range of pore sizes from meso to small macro. So we get a good range on different pore sizes using the BET analyzer. And we can also get down to specific surface areas as low as 0.001 meters squared per gram, which is quite small. So we get a pretty good wide range of measurements using that instrument. I also use the atomic force microscope, and it's in tapping mode because so many of these surfaces are quite squishy that if we use non-tapping mode, it will hurt the sample and mess up our measurements. And so it measures the roughness surface index, which is another way to determine roughness, and that's the actual surface area over the projected surface area, and attain some really cool topographical images. So going into my research, I care about attaining the physical properties of a wide range of indoor surfaces, and to answer the question on how does surface area and other physical properties impact indoor air quality, actually within the literature, there's quite a limited number of measurements done on the physical properties of indoor surfaces. So this is also helping to expand the literature and obtain more actual numbers that people can use to explore other questions relating to the physical properties of surfaces. As mentioned, I used the BET specific surface area analyzer and atomic force microscope. And what I found is that using specific surface area increases the surface area available for absorption, like expected, that the paint changes the physical properties of the base surface. And then now one surface can represent all indoor surfaces, so it's important to consider each surface individually. To start, I have 4 different scenarios. And so this is all the surface area of our test office space that we use for the Tech Indoor Biogeochemical Project. And so in the first scenario, it's just the geometric surface area of that room, and that's 83 meters squared, with the primary surface type being wood because of all these wood shelvings that it actually ends up having most of the surface area in the room compared to the walls. In the next scenario, I incorporated dust into this geometric measurement. While we don't consider dust a surface, it actually is a quite important contaminant considering the many different exposure pathways it has. Not only can we inhale dust, but we also can ingest dust and even touch it, and so we have thermal exposure, and it's really important, especially for small children that spend a lot of time on the floor and understanding that exposure. And I saw that there's 3 meters squared of dust in that room, so it increases the surface area. And that's a bit more dust than I personally would like to know that's in my indoor space. So, might take this as a sign to vacuum more often. And then the next 2 scenarios, I use specific surface area. The difference between these scenarios is that I have the same test room, but I'm changing what the ceiling is. So hypothetically, in the first ceiling, the ceiling is drywall. Drywall is a common ceiling material for residential homes. So this is something that might be more representative of a residential location. And so with that, we see the surface area increase by 3 orders of magnitude. So that's quite a bit increase in surface area. Now the primary surface material is going to be drywall, followed by wood, then the carpet. In the next scenario, it's going to be just a normal office space, so it's the same room, but now I use drop ceiling, ceiling tile as the ceiling material. That's typically found in office environments, and we see the surface area increase by 4 orders of magnitude, and 96% of that surface area is coming from the ceiling tile itself. And so this really demonstrates that by just changing one surface material, we can decrease the surface area of the rooms quite a bit, and thus decrease the capacity of these surfaces, potentially increasing the indoor air quality. The next point is that paint changes the physical properties of surfaces. And so there tends to be 2 different trends we see here. So paint is able to fill the pores, and by filling the pores, we see a decrease in surface area. And so this really is happening with permeable surfaces. Paint also, through the film formation process, creates these globules on surfaces. And so actually, because of those globules, we see either a no change or a positive change in roughness. And so with that, we kind of have to consider what the base material is of that we're painting to actually understand the impact paint is having. Because for an impermeable surface, there are no pores to fill. It's not being absorbed into the material. All we're having is that roughness increasing from the globules in the film formation process. And so that's increasing surface area quite a bit. And that's really important because actually, while we don't typically paint glass indoors, though me as a child always had those like window painting competitions around the neighborhood. So with that one exception, I guess, we don't typically paint glass. And so when we try to study the impacts of paint, that's typically done on a smooth surface, something like glass or Teflon, and that might not typically behave like paint does indoors. And we have to actually, when studying paint, when thinking about paint, we need to consider what is being painted, not just the paint itself. And additionally, I also looked at stain because stain wood isn't just painted indoors, it can also be treated with stain. And that has a really interesting trend because we see an increase in surface area but decrease in roughness. And I'm not fully sure why stain behaves like that, though it does create some questions that stain should be investigated more in terms of how it impacts indoor air quality, and also can help lead insight on whether painting or staining might be better in terms of indoor air quality perspective. Finally, and this kind of all leads to that we have to take careful consideration of what indoor surfaces we're using or thinking about in modeling experiments or design buildings. Here is all these fun topographical images I've taken with the AFM. And so we can see just from these visualizations here that they are quite different and none of them are going to end up behaving the same because these physical properties have real impacts. Not to mention that the chemical properties of surfaces are also going to have additional impacts. So we really have to consider whether it's in models separating out, not just collectively saying indoor surfaces, but being like walls versus carpeted floors, or in experiments like I mentioned with paint, understanding the base material, but also understanding being able to study different surfaces and understand why different surfaces behave a certain way. And then ultimately, more broadly, when designing indoor buildings, are we able to select better building materials that can help improve indoor air quality, or apply paint that is going to then decrease the capacity of surfaces, for example, and various choices when it comes to how we improve our indoor environment to improve indoor air quality. I'm going to go into my second research project here. And so this project primarily focuses on obtaining direct measurements and to measure the bulk capacity and partitioning behavior of surfaces. And so this is one that I'm currently working on. And so the key questions I have right now is how much is stored in different surfaces over time for different compounds, and then how much of that stored gas is re-emits and at what rate. I'd use the isotope labeled injection method. So what I mentioned before, when we inject an isotopically labeled compound to trace, I'd be able to trace them in the surfaces. And I measure that with an isotope ratio mass spectrometer. That instrument can measure quite small differences in carbon-13 versus carbon-12. That can give me quantitative data that I can use to know how much is being stored. And the results I have so far is that I've been able to actually quantify the mass of a stable isotope tracer in ceiling tile and gypsum. So my method had been proven to be successful, and I can actually obtain these direct measurements. And with this preliminary data, I have evidence of diffusion occurring within ceiling tile, which is super cool and interesting, and is going to, this makes me excited for future experiments. So to start, I'm going to have to get a little nitty gritty into isotopes right now so that we understand how we got here and why these direct measurements work. And so to get these direct to get quantification of the gas compound in indoor surfaces, we have to use the mixing model. And this mixing model is a mass balance model that takes the signal of your sample and mass of sample, and it equals a combination of the signal of the gas and mass of gas with the signal of the surface and the mass of the surface, or material in this case. And when we talk about the signal, these are carbon isotope ratios. And what that is over on the right is the amount of carbon-13 over carbon-12 in your sample, divided by carbon-13 over carbon-12 in the standard, minus 1 times 1,000, because we're talking about very, very small differences here when we talk about isotopes. And this seems really complicated, but all it is that the key thing to know here is that if it's a negative number, it means it has less carbon-13 than in the standard. And if it's a positive number, it has more carbon-13. And so the more positive we get, the more enriched the sample is, which is what I'm trying to push the samples to be as positive as they can be, so I can actually measure the amount of gas in the surface. And so first thing we need is to know the signal of the materials. Anything that contains carbon, even just 1%, is going to have a isotope ratio, and we need to know what that isotope ratio is. So for various indoor surfaces, I did a wide range of organic and inorganic surfaces and different layers of them. And we found not only are many of these the first isotope ratios for many of these surfaces, but they also have quite low variations, which is a really good sign, because when I try to push the isotope ratio, the sample signal, to be more to positive, it's going to be easier to do so because there's less variation. There's one exception, which is the carpet fibers middle. That layer of carpet has it's quite heterogeneous with all the different components of it, and so that's why you get such a wide range of signal there. But for the most part of all the other surfaces, we're able to have low variation, which is super great, and we have the numbers to be able to use the mixing model and quantify the amount of gas in there. The next step is actually injecting the gas into the room. So we have different surfaces. I put different surfaces in there and I injected the tracer in there. And in this case, this is urea. And this isotopically labeled urea has a signal of 8,008,500. That is crazy high, super positive. And so with that high number, I'm hoping to try to push my numbers as much as possible. But we also can acknowledge that only micrograms of this gas is going to end up being emitted on these surfaces. So we're not going to see anything crazy too high, but we need to know the signal of the gas to know the mass of the gas, and then we also inject it indoors. Once I remove my samples and grinded them into a powder, I weigh them out with a microbalance. And in that microbalance, I'm able to get the mass of the sample. And that mass of the sample is going to equal the mass of the gas and the mass of the material combined. The next thing I've done is able to actually measure what's the signal in the sample now. And what is great is that all these surfaces that I measured here are above the limit of quantification. And so that's amazing. That means now I can actually be able to quantify these surfaces. And if we see in this graph here, the error bars are the 10 times the standard deviation. So we see that all these, after the addition, that all these surfaces are outside of the limit of quantification. And so we are actually able to quantify. And now that we can, this map, and we applied the mixing model, and we are able to actually obtain measurements of the gases in these surfaces. These are the raw quantities of 13C urea in the surfaces. And so we see here that the inner sealing tile actually has greater mass than the outer sealing tile, which is really interesting because only after 2 hours of exposure that already the inner sealing tile is containing more. We can expect some desorption coming off from the outer sealing tile causing that, but still it's quite surprising that we're already seeing diffusion occurring. And I do believe the pores in the sealing tiles, if you remember in the earlier picture, all the little holes, that they really play a large role in that diffusion process. And so now that we actually have a method that works, which is amazing, I can finally start doing some experiments that address the key scientific questions I want to get at to hopefully understand surfaces better and actually improve indoor air quality. And so with that, I'm going to be exploring the capacity and gas surface interactions of 5 different indoor surfaces. I'm going to be exploring ceiling tile. Ceiling tile has high specific surface area, so it's likely going to have high capacity and also has some interesting preliminary data on diffusion that's occurring. So I think it's going to be a really interesting surface to explore. I do 3 variations of drywall. I have painted drywall, non-painted drywall, and just the gypsum. The gypsum is the inner part of the drywall that is kind of like that powdery rock on the inside. And so with that, I'm trying to also explore the diffusion that's occurring, seeing which layer of drywall is limiting the diffusion, or does that not play a role? And so with that, I have 3 different variations just to explore the capacity and the diffusion that's occurring. I'm also going to do dust. Dust, as I mentioned, has a lot of different exposure pathways and is more prevalent indoors than we would want. And so just understanding how much of these compounds are also being absorbed to dust is important to understand. And I chose 3 different gas phase compounds. They're all within the carboxylic acid series. We have acetic acid, butyric acid, and octanoic acid. And so they all have different, as I mentioned earlier, octanol air partitioning coefficients. And that's going to change how much they're going to prefer to partition with the surfaces. So we're getting a range of different KOAs to explore these interactions. And what's also interesting, at least from a diffusion perspective, is that smaller compounds tend to diffuse faster. And so it's interesting to see whether the lightness of one compound is going to outweigh the lower KOA, less partitioning. So it's going to be interesting looking at those opposing trends with these 3 different gas phase compounds. And so I hope at this end of this presentation, I've taken away that the choice of surface material matters when studying indoor chemistry and understanding indoor air quality. And the literature shows that indoor surfaces impact indoor air quality, whether that's through the capacity of these surfaces or their partitioning behavior. And I'm currently trying to explore how these surfaces can impact indoor air quality so we can make better decisions to improve our surface materials and indoor environments by looking at the capacity, so the surface area available for absorption, and also by obtaining direct measurements of what's being stored in the bulk material, along with understanding the partitioning behavior, such as the desorption and re-emission. Over long periods of time, I'm going to go up to weeks and months for different compounds, and then the diffusion that's occurring among these surfaces. Thanks for listening to my presentation, and I'm open to any questions.
Awesome. I have so many questions. I'll start us off, but if you have a question, feel free to type it in the chat or press the raise hand button. It should be at the top. So one question is, are these emissions or like degassing continuous, or are there specific events or like something to trigger a release, like temperature or yeah, like changes in temperature, like if I put a pot or a hot mug or something, would that do something like that? Yeah, I'm just trying to think about it.
Yeah, that's a really good question. And so I know in terms so there are a part that's continuous. They want to maintain an equilibrium essentially. And so because we're constantly ventilating out, it's going to also be constantly desorbing out. But I also do feel like temperature tends to create a more energetically favorable place to have that desorption. And so it's going to more readily happen. So I'm not sure on the literature in terms of like how temperature plays a role, but I do suspect that when you apply at greater temperatures, we're going to see more desorption also happening. I also think in terms of like, there's also reactive uptake. So the reactions can be occurring. If there's reactions occurring in the gas phase, that's going to maybe favor some going more into the gas phase or more into the surface phase. Likewise, with typically we can see if there's reactions that are happening on the surface, that's actually going to pull more of the certain gas phase, like acid-base reactions that's happening on the surface. And that's going to then pull more of the gas phase into the surface. So it kind of goes both ways depending on what the chemistry is occurring. So
Okay.
in that way, it gets quite complex, but
Yeah. So if there was like a sunbeam hitting a counter for a while, like would that be enough energy to warm it up?
yeah, I mean, like I would say that can provide some substantial energy that can maybe promote a certain way that can change what's occurring. And also what's really interesting with like the sun being and with indoor environment, that can also create maybe specific reactions that's only occurring there that might not occur other places. Because indoor, we typically don't get that photochemistry, but we do see that photochemistry in like places like our windows or close to the windows or our lights, which can also then change different, it could have different reactions, different contaminants come from it, and also maybe change the concentrations or the re-emit, like how much is being re-emitted out. So
Okay. Anyone have a question? Because I want to keep going. Okay. So, are there any health standards for indoor air?
think I don't think to my knowledge, but I could be wrong.
No, I
Um,
think that sounds right to me.
yeah, I feel like within the literature, people are like talking about like some like, I think maybe applying outdoor standards to indoor and seeing how that compares, but I don't think that's very equatable, if that makes sense, because there are like longer exposure times indoors. And so
Right.
that's going to impact.
Yeah. And that gets this other question of would this exposure be considered chronic or acute?
I think in terms of specifically when I talk about these surfaces and the role the surfaces play, I would say these are chronic exposure. There are cases that's going to have acute exposure, and so we could talk. There's literature on like cooking events or cleaning events, like cooking for Thanksgiving emits a lot of particles because of just all the various cookings that are happening, and that's more of an acute event based off that cooking event, right? We only cook Thanksgiving once or twice a year, right? But I would say the role in which these surfaces plays are going to be doing a chronic exposure, and I think largely a lot of indoor air quality issues when we talk about background and just kind of like these overtime emission sources are going to be a chronic exposure source. It's really just, I guess, specific emission events are going to cause acute exposure. So,
Okay. And then for my last question is about the gases. So I sometimes put my towel to dry on the top of the door, and sometimes I can tell that it smells like the food we cooked yesterday. And so, yeah, how do we, like when these things are degassing, are they eventually making it up to the top or are they more well mixed?
well, it kind of depends on the ventilation of your home too, if that makes sense.
Hmm.
I'd say generally, I think we would say that they're ending up becoming well mixed, but also like the home itself is dynamic. So like it could be well mixed in your kitchen and then like over time maybe go to your bathroom and it takes some time or some of it goes to your bathroom. So it's not what well mixed is kind of hard. It's not well mixed around your home. It may be well mixed around the room, for example. And so I wouldn't and like, but again, with cooking, if you have like a vent over it, in theory, we're trying to ventilate it out or sending it to the top to decrease it getting other places. So it really just depends on what the ventilation is at your home. So
And I guess one thing would be, do you have any recommendations that for us of keeping our indoor air quality good, or I guess of cleaning our surfaces or anything like that?
Yeah. So one of the best things to do is that when you are doing something that's an emission event, and so we count something as like cooking or even cleaning as an emission event because they're going to release different volatile organic compounds and particles. Make sure you have some ventilation that is going on when doing so. By like shown in the site, when we have enhanced ventilation, we're going to decrease that quality. That's going to decrease the amount that's getting on the surfaces because we can ventilate more out, less is actually getting around onto our surfaces. And so that could even be from opening our windows to having a nice little like hood over our stove. Various different things can help that. We also, in terms of cleaning surfaces, especially so I talked a lot about what I would call permeable surfaces. These surfaces that are sticky, that are holding into the bulk material. But when we think also about like a kitchen space again with that emission event, there's mostly like these harder materials that aren't having that diffusion. They're going to form instead surface films, which is a whole like big area of research that I didn't even get into. That's really easy to clean by just wiping it down. And we can just get rid of that by just cleaning our surfaces, by wiping down our floors, like our hardwood floors. And so, yes, it is really good to make sure we're cleaning our surfaces to decrease the amount in the surfaces. It's a little harder to address something that maybe like our ceilings or our walls that are going to end up being a bit more sticky. But for a lot of different surfaces, we can actually address by cleaning. And so that's another really positive thing we can do. Those are probably like the big two in terms of what like you can do right now to decrease your or improve your air quality, decrease the contaminants in the air. More broadly, like I'm hoping my research can kind of look into maybe if we apply certain types of paint or develop certain paints, maybe we can stop certain materials from being able to store so much if we have maybe a like paint that really slows the diffusion that almost behaves like glass in a way. So
Ooh, cool.
yeah, that's like kind of like I'm hoping my data shows that, but we're going to see if like or just kind of like see that this encourages a route because we have like low VOC paint now made
Mhm.
because like people complain about the smell, people complain about it the VOCs emitted from paint ends up causing exposure. But if we can I think we can modify paint to improve indoor air quality, and that's something that I consider accessible to quite a lot of people versus chopping out our walls. So
Yeah, cool. Um, Anyone else have questions? Okay. So if you do have other questions, feel free to reach out to Rachel. If you're comfortable, feel free to put your email address on the
yeah.
chat. But yeah, thank you everyone for coming to these Lunch and Learns. We hope you have wonderful holidays and a great new year. And we will see you next year. Hopefully, we'll start in January, but likely not, probably February for our Lunch and Learns again. And if you have any recommendations on people that you would love to see present, please send them to our email address. Or if you would like to present, pitch us a webinar idea and then we can discuss. But again, thank you so much, Rachel. Good luck with classes if you still have them.
Thank you so much. Yeah, next week's finals week, so gotta get through
You
that.
got this.
Yeah,
You got this.
thank
All right.
you.
Thank you,
Thanks.
everyone.
You. Thank you.